Hello. In the last lesson we talked about how to find the electric field due to point charges. In today's lesson we will use Gauss's law to find the electric field due to extended charged objects. Now, what are extended charged objects? Well, of course, an object like this is not a point charge. If you have an object like this given a certain amount of charge, this is an extended charged object. Well, if you have a spherical object as big as this is not a point charge. This is an object that is an extended charged object. Well, this is what we achieve to do today by discussing Gauss's law. Gauss's law is an important law in electricity. In order to study the electric field due to extended charged objects, we define some important terms. Let's look at these important terms, what they are. The first term is linear charge density. Linear charge density, what does that mean? It means the charge per unit length of the object. If I have an extended charged object like this, which carries a certain amount of charge, what is the charge per unit length? That is called linear charge density. Now, what is the unit for measuring linear charge density? It is measured in coulombs per meter. And you see, we represent linear charge density by the Greek letter lambda. Alright. If Q is the total amount of charge on an object like this of length L, what is the linear charge density? Total charge is Q, total length is L, therefore charge per unit length is Q over L. Lambda equal to Q over L. The second term that we will be using is surface charge density. A certain amount of charge Q is distributed over a given surface. What is the charge per unit area? We will represent that by the Greek letter sigma. And it will be measured in coulombs per meter squared, charge per unit area. An amount of charge Q, if an amount of charge Q is distributed over an area A, what will be sigma equal to? The surface charge density sigma equal to Q over A, charge per unit area. The third term we will discuss is volume charge density. What do you think volume charge density is? A certain amount of charge is distributed over a volume. Now you must distinguish between surface area and volume. A certain amount of charge is distributed over a volume, then charge per unit volume is called volume charge density. We represent that by rho, and it is measured in coulombs per meter cube. Now, how will you calculate rho? If a certain amount of charge Q is distributed within a volume V, then rho equal to Q over V. Volume, the amount of charge per unit volume is rho. Alright, let's review a concept that we discussed in our last class. A very important concept, and that is the concept of electric field expressed in terms of the electric flux. Now, how many of you remember the electric field at a point defined using the electric flux? Can you recall that definition? Electric flux is represented by phi. Flux is a measure of the total number of lines of force crossing a given area An electric field at a point is the flux crossing at right angles to unit area that contains that point. Is that right? So electric field is the normal flux per unit area. In other words, E equal to flux per unit area. Remember, the flux phi must be the normal component or the normal flux. And therefore, the total flux crossing a given area, what will that be? If E is flux per unit area, what is the total flux crossing a given area? That will be phi equal to E times A. We will be using these concepts in developing Gauss's law. Now, if the electric field lines make an angle theta with the surface A, then you need to find the normal component of the flux, the component of the flux at right angles to. Now, if the flux makes an angle theta with the surface, then you need to find the component of that flux at right angles to the surface. That will be phi equal to EA cos theta. You can see that will be the component normal to the surface. Now, we will represent the electric field that is the normal component as E sub n. So, then we have the total flux crossing any given area is the normal electric field multiplied by the area. Alright, so keep these two equations with you. We will be using that as we go on. Okay. If a surface contains more positive charge than negative, do you remember we talked about the number of lines of force coming out or going into a charge? Suppose you have a certain surface. Well, let's say this is a surface, a spherical surface. And this spherical surface contains inside some positive charge. That means flux will be coming out of it. Is that right? Because lines of force will be originating from a positive charge. If this surface contains some negative charge, then flux will be going into the surface. Well, if a surface contains more positive charge than negative, so inside the surface there is more positive charge than negative, then there will be a net flux leaving that surface. There will be a net flux leaving the surface. Remember, there will be lines of force going in and there will be lines of force coming out. If the net charge inside is positive, then the number leaving the surface will be greater than the number going in. That's what this means. If a surface contains more positive charge than negative, there will be a net flux leaving the surface. In the same way, if a surface contains more negative charge than positive, then there will be a net flux entering the surface than leaving it. That means the number of lines of force entering that surface will be greater than the number of lines of force leaving that surface. We talked about that in the last class. If a surface contains no net charge, what can you say about that surface? About the flux entering or leaving. The amount of flux entering will be equal to the amount of flux leaving. There will be no net flux entering or leaving. All the flux that is entering a surface will also leave if there is no net charge inside that surface. Now, these three statements are key to understanding Gauss's law. Now, here I have explained that. Now, here you have a positive charge, and a negative charge. So the net charge inside is 0. which means the number of lines of force leaving, there are some lines of force leaving, is the same as the number of lines of force entering. That means the net flux through this surface is 0. Now, how about this diagram? Now, the positive charge is bigger than the negative charge. That means there is a net positive charge inside that surface. What that means is the number of lines of force leaving will be more than the number of lines of force entering. There will be a net flux leaving the surface if the net charge inside the surface is positive. The number of lines leaving the positive charge are greater than the number entering it. Alright, let us consider a positive charge Q placed inside a spherical surface of radius r. Here is a spherical surface. Imagine when I draw it, it looks like a flat surface, but it is a spherical surface of radius r, and you have a charge Q inside there, and I have used a positive charge Q there. Alright, now the electric field at any point on the surface, you choose a point there, the electric field at any point on the surface of the spherical shell will be at right angles, because all lines of force or field lines that may originate from here will all be at right angles to the surface. So the electric field at any point on the surface will be at right angles to the surface and will be given by, can you tell me what will be the electric field at that point? If you remember the basic equation, the electric field at a point, distance r from a charge q, is kq over r squared. Is that right? Here r is the radius of the spherical surface. So if you have a spherical surface like this that carries a charge q inside, then the electric field at any point on the surface will be at right angles to that surface, and its magnitude will be E equal to kq over r squared. So En, what does En stands for? It stands for the normal electric field equal to kq over r squared. Now, what is the net flux leaving the spherical surface? How can you write an expression for the net flux leaving the surface? Well, the net flux leaving the surface is E times A. Why? We talked about this because electric field is defined as flux per unit area. So, electric flux is flux per unit area. If this is the unit area, then the electric field is the flux crossing that unit area. To find the total flux leaving the surface, we multiply the electric field by the surface area, which is A. Anybody tell me what is the surface area of a sphere? Well, so now our E is kq over r squared. Is that right? E equal to kq over r squared, and A is the surface area. Now, what is the surface area of a sphere? Well, some of you might know. The surface area of a sphere is A equal to 4 pi r squared. So, let's replace this A by 4 pi r squared, and that will then give you a measure of the net flux leaving the spherical surface through the entire area. So phi net, the net flux leaving the spherical surface, will then be kq over r squared times 4 pi r squared. And you can see r squared and r squared cancels. That gives us 4 pi kq. Very important relation. The net flux leaving a spherical surface is 4 pi kq. In fact, this can be used as an expression for the net flux leaving any surface. You can see it is independent of the radius. The radius simply cancels. Alright. You know that we had earlier used k equal to 1 over 4 pi epsilon naught. That constant k, which we normally use as 9 times 10 to the 9. You remember? It is 1 over 4 pi epsilon naught, where what is epsilon naught? It's the permittivity of free space. Alright, let's replace this k by 1 over 4 pi epsilon naught. And what does that give you? You can see when k is replaced by 1 over 4 pi epsilon naught, the 4 pi and the 4 pi cancels. It will give you phi net equal to q over epsilon naught. A very good equation. The net flux leaving any given surface is q over epsilon naught, where q is the total charge on the surface and epsilon naught is the permittivity of free space. You should remember it in both forms. Phi net equal to 4 pi kq, and replacing your k by 1 over 4 pi epsilon naught, it gives you phi net equal to q over epsilon naught. Alright, let's now develop Gauss's law using this. Now, if Q inside is the net amount of charge within a surface. Now, from now on, we're going to call the amount of charge inside a surface as Q inside. Alright, then the net flux leaving or entering the surface. When I say the net flux, well, it can be the net flux entering or the net flux leaving. So, what is the expression then? Phi net equal to 4 pi k q inside. That's the same expression we derived in the last slide. Or this will be q inside divided by epsilon naught. Is that right? Q inside divided by epsilon naught. The net flux either entering a surface or leaving a surface equal to q inside divided by epsilon naught. Now, this is the statement of Gauss's law. A very simple statement. The net flux leaving or entering a surface is given by 4 pi k q inside, where q inside is the amount of charge inside the surface. Also, it can be written as q inside divided by epsilon naught. Alright. And the value of epsilon naught is 8.85 times 10 to the negative 12 coulomb squared per Newton per meter squared. We can now use this to solve problems. Alright, let me give you a couple of scenarios. Surfaces S1, S2 and S3 all enclose the same amount of charge. Can you watch this one? This is the amount of charge. Surface S1, surface S2 and surface S3 are all enclose the same amount of charge Q. Alright, compare the net flux leaving each surface. Well, is there any difference between the net flux leaving the surface S1 and leaving the surface S2? If you notice that all the field lines leaving the surface S1 will also leave the surface S2, will also leave the surface S3. You see that? The net flux leaving any of these surfaces is the same, namely 4 pi k q inside, because each of these surfaces has the same charge q inside. Alright. What is the net flux crossing the surface shown below? What is the net flux crossing the shaded surface? Anybody tell me? Think about it. All the lines of force, all the field lines entering the surface will also leave it. The flux entering the surface is the same as the flux leaving the surface. Therefore, the net flux crossing the surface or the net flux entering or leaving equal to 0. Is that right? Yes. Let's do an example. An electric field is E equal to 300 Newton per Coulomb I. You understand that it is an electric field in the positive x direction for x greater than 0 and E equal to negative 300 Newton per Coulomb I for x less than 0. That means to the right of the origin you have an electric field directed to the right. To the left of the origin you have an electric field directed to the left. Obviously, it means that field is created by a positive charge at the origin. Is that right? Okay. A cylinder of length 20 centimeter and radius 4 centimeter has its center at the origin and its axis along the x-axis such that one end is at x equal to 10 centimeter and the other at x equal to negative 10 centimeter. Part A. What is the flux through each end? Well, let's picture the problem. Look at this. Now, this is the origin. The field to the right of it is 300 Newton per Coulomb, positive x. And field to the left is negative 300 Newton per Coulomb I. In other words, it probably is due to a positive charge here. And now, there is a cylindrical surface lying so that the origin is inside that cylinder. And one end of the cylinder is at negative 10 and the other end is at positive 10. And we need to find the flux through each end. What is the flux crossing that end? Now remember, you must now understand the amount of flux crossing an area. If this is the area, the amount of flux crossing this area will be the electric field multiplied by the area. Is that right? Because the definition of electric field is flux per unit area. So flux crossing an area is electric field that is the right at right angles. The electric field at right angles to the area multiplied by the area. Alright, so can we find the flux crossing each of these ends? Well, you know that the diameter of the radius of the cylinder is 4 centimeter. So the area of cross section of one end of the cylinder. Remember that cylinder, one end of the cylinder is a circle and the radius of that circle is 4 centimeter. Therefore, what is the area of cross section? A equal to pi r squared, where r is 0.04 meter. That will be pi times 0.04 squared. That is 0.005 meters squared. So this area is 0.005 meters squared. And the electric field crossing that area at right angles is 300 Newton per Coulomb. Therefore, phi equal to E times A. And that will be 300 Newton per Coulomb multiplied by 0.005. That is 1.5 Newton meter squared per Coulomb. Now, we don't need to take the negative sign in calculating the flux leaving a surface. The negative sign simply indicates that the field is directed in the negative x direction. So the flux leaving the left end of the cylinder is this. Also, the flux leaving the right end is this. Therefore, if I ask you, what is the total flux leaving the cylindrical surface through both ends? It will be the sum of this, which will be 3 Newton meters squared per Coulomb. So, phi right equal to phi left equal to 1.5 Newton meters squared per Coulomb, or the total flux leaving the cylindrical surface through the two ends will be the sum of the two. Alright, B part. What is the net outward flux through the entire cylindrical surface? Now, this is actually a cylinder. Now, the electric field is that way and this way. Now, tell me, what is the flux crossing the cylindrical surface? Are there any field lines crossing the cylindrical surface? No, there are no field lines crossing the cylindrical surface. That means there is no flux crossing the cylindrical surface. So what's the answer for that B part? The flux through the cylindrical surface is 0. There are no field lines crossing the cylindrical surface. Now see, what is the net flux? What is the net flux therefore out of the cylinder? What is the total flux coming out of the cylinder? The total flux coming out of the cylinder is the flux coming out of the left end added to the flux coming out of the right end, which is 1.5 plus 1.5, 3 Newton meter squared per coulomb. Alright, now the question is, what is the net charge inside the cylinder? All we need to do is, we go to the Gauss's law. What does Gauss's law say? The Gauss's law says, phi net, the net flux either entering or leaving a surface, equal to 4 pi k q inside, or q inside divided by epsilon naught. Phi net equal to q inside divided by epsilon naught, and phi net is 3 Newton meter squared per coulomb. So we can write q inside equal divided by epsilon naught equal to 3. Therefore q inside will be 3 epsilon naught, and we know the value of epsilon naught, 8.85 times 10 to the negative 5. Therefore q inside is 2.66 times 10 to the negative 11 coulombs. So obviously this electric field is due to a charge at the origin which has this value. That is the amount of charge inside that cylindrical surface. You see, Coulomb's law is a very neat way of calculating electric fields and electric charges. Alright, let's now go and talk about how Gauss's law can be used to find the field at a point due to an infinite plane charge. What is an infinite plane charge? Well, I can't really show one. Well, this is the best I could come up with for an infinite plane. Now remember, when you say an infinite plane, the length and width of it will extend to infinity. And we want to find the electric field at a point due to an infinite plane charge. Alright, now watch this one. This is the infinite plane. I want to find the electric field where I'm pointing. And that is our task. We want to find the electric field over here. And look at what the method that we're going to follow. We can use Gauss's law to find the electric field near an infinite plane charge. Consider a plane charge of surface charge density sigma. Well, you need to remember what that is. What is surface charge density means? Charge per unit area. So here we have an infinite area, infinite plane of surface charge density sigma. In other words, if you take all the charge on it and divide by the total area, that will be our sigma. Alright, now here I have drawn a picture of that. This is the infinite plane. Of course, it has to extend in all directions. It is carrying a certain amount of charge. We need to find the electric field, say at a point where I'm pointing now. We need to find the electric field at a point near it. Alright, field lines leave the upper as well as the lower surface. Watch this. The electric field lines will be leaving the upper surface as well as the lower surface. Now, because the charge carried by this plane surface is positive, there are field lines leaving the upper surface upward and leaving the lower surface downward. Is that right? That means if you now want to find the net flux leaving, it will be the flux leaving on the top plus the flux leaving below. Alright. The field E has the same magnitude but opposite direction at points at the same distance above and below the plane. Is that right? If at any point above the field is positive, directed upward, at any point below the field will be directed down. This will be downward and negative. In order to find the field at a point, we choose a Gaussian surface. Now, this is the standard method we're going to use for every problem using Gauss's law. We're going to choose a Gaussian surface which encloses a small portion of the charge carried by the plane and that contains the point. Now, I need to explain that. Now, I want to find the electric field at a point near this surface. So what I'm going to do is, I'm going to use a Gaussian surface. Now, the surface I'm going to use is actually like a pillbox. Now, look at this. Now, I'm going to take a Gaussian surface which encloses a certain amount of charge of the plane surface. And also, it contains the point where I want to find the electric field. You see that? So, we take a Gaussian surface which contains the point where we want to find the electric field, which encloses a certain amount of electric charge of the plane surface. Alright? That's what we're going to do. And this is the pillbox that I have chosen. The Gaussian surface we have chosen is in the form of a pillbox-shaped cylinder. Since the curved surface of the cylinder is parallel to the field lines, there is no flux crossing the curved surface. What it means is, because the field lines are vertical, upward or downward, there are no flux crossing the curved surface. The flux only crosses the flat surface. That means the flux is crossing only that flat surface, not the curved surface. Okay. If A is the area of the face of the cylinder parallel to the plane, and E is the electric field perpendicular to it. So if A is the area of that flat surface and E is the electric field at a point on it. Remember, we are looking for the electric field at a point which is on that surface. And so we are looking for that E. So if E is the electric field at a point on that surface and A is the total area, then the net flux crossing that surface will be what? Will be E times A. Will be phi equal to E times A. Now, the flux crossing upward will be E times A. The flux crossing downward will also be E times A. That means the total flux leaving the pillbox will be 2 times EA. Alright. Since the flux leaves at both surfaces, upward and downward, the net flux leaving the cylindrical surface is given by phi net equal to 2 EA. And EA upwards, the same quantity downwards, the total flux leaving is 2 times EA. Since A is the area of the plane charge inside the Gaussian surface, can you now tell me, this pillbox contains the amount of charge the amount of charge on an area A, and the surface charge density is sigma. Therefore, what is the amount of charge contained inside the pillbox? The amount of charge contained inside the pillbox is this area A multiplied by sigma, which is the surface charge density. So, the amount of charge that is inside the pillbox is A sigma. And now, we come and use our Gauss's law. Q inside, therefore, equal to A sigma. The amount of charge inside the pillbox is that area multiplied by charge per unit area sigma. Alright, what's Gauss's law? Phi net equal to Q inside divided by epsilon naught, and Q inside is A sigma. Phi net is 2EA. Let's put that together. So 2EA equal to A sigma divided by epsilon naught. So on the right side, on the left side, if you divide both sides by A, the A will disappear. That means the area of the pillbox is not important. You can take a big pillbox or a small pillbox. That area will not affect our calculations since it cancels. Therefore, can you solve for E from there? What is E equal to? E equal to sigma over 2 epsilon naught. You see how easily we obtained the equation for electric field near an infinite charge, infinite plane charge, is sigma over 2 epsilon naught. The field near an infinite plane charge is E equal to sigma over 2 epsilon naught, a very important and interesting equation to remember. And that will be the same as 2 pi k sigma, is that right? Because epsilon naught is the same as 1 over 4 pi k, because k equal to 1 over 4 pi epsilon naught, or epsilon naught is 1 over 4 pi k. Using that, you get sigma over 2 epsilon naught is the same as 2 pi k sigma. Let's do another problem. An infinite plane of surface charge density sigma equal to positive 4.5 Newton nanocoulomb per meter square lies in the YZ plane, and a second infinite plane of surface charge density sigma equal to negative 4.5 Newton per nanocoulomb per meter square lies in the YZ in a plane parallel to the YZ plane at x equal to 2 meter. Find the electric field at x equal to 1.8 meter and at x equal to 5 meter. Well, this time we have two plane surfaces in the YZ plane. Can you visualize how they look? Well, look at these two plane surfaces. It will look like this. One is at the origin, the other is at x equal to 2 meter, and we need to find the electric field at x equal to 1.8 meter. That means at a point in between the two planes, and at x equal to 5 meter, that will be outside. Let's draw a diagram of it. Now here's the diagram. This is the first plane, infinite plane of surface charge density positive 4.5 nanocoulomb per meter square, and this is the other plane that has a surface charge density negative 4.5 nanocoulomb per meter square. You know that the electric field will be inside from the positive to the negative. Is that right? Yes. Okay. This has a surface charge density sigma, and this has a surface charge density negative sigma. Now the field lines start at the positive plane and end at the negative plane. In the space between the two planes, the field due to the positive plane is in the same direction as the field due to the negative plane. You see, if you take that point, the field due to the positive will be directed away from it. The field due to the negative will be directed towards it. Both are in the same direction. That means both those fields will add up. Now, between the two planes, these two fields add up. Now tell me, using Gauss's law, if you remember, what is the expression for an electric field at a point close to a charged infinite plane? Field at this point will be sigma over 2 epsilon naught. So the field near an infinite plane charge is E equal to sigma over 2 epsilon naught. That means the field due to the positive plane will be sigma over 2 epsilon naught, and the field due to the negative also sigma over 2 epsilon naught, both directed in the same direction. Therefore, the field at any point, it doesn't matter which point you take, if you take any point in between, the field will be the sum of these two, which will be sigma over epsilon naught. I want you to remember this because we will be using this. If you have two planes that carry electric charge, the electric field at any point between those plane charges will be sigma over epsilon naught, where sigma is the surface charge density. Therefore, what is the field at x equal to 1.8 meter? X equal to 1.8 is a point inside the region between the two planes. Therefore, the field will be sigma over epsilon naught. And we know the values of both. Sigma we are given, epsilon naught we know, and that's equal to 508.5 Newton per coulomb. Alright, let's find now the field at x equal to 5. Now, to the left of the positive plate, tell me what is the direction of the electric field to the left of the positive plate? To the left of the positive plate, there will be a field due to the positive plate directed to the left, and there will be a field due to the negative plate directed to the right. So at any point here, there will be field due to the positive and field due to the negative, but they are in the opposite direction. That's right. So what happens? They will cancel each other. Suppose these red lines indicate the field produced at any point outside due to the positive charge, and the green lines indicate the field due to the negative. They cancel each other. That means on both sides. Now come on the right side. The field due to the negative and the field due to the positive will cancel, and therefore any point outside on the left, outside on the right, the field will be 0. There you are. So at x equal to 5 meter, the electric field, the net electric field will be E1 minus E2, that will be 0. Let's now talk about field due to a spherical shell of charge. What is a spherical shell? Well, actually a basketball is a good example of a spherical shell. Inside it is hollow, and we have a certain amount of charge distributed on the surface of the basketball. We need to find the electric field at any point inside or outside due to the charge on the spherical shell. Alright. Now consider a spherical shell of radius r that has a total charge q. There you have a spherical shell of radius r. Now look at only the yellow shell. Don't look at the blue now. We'll talk about that as we go on. It carries a charge, a total charge q. Its radius is r. By symmetry, the field due to this charge must be radial, and its magnitude depends on the distance from the center of this charge. Now, You see, at any point, anywhere here, the field depends on the distance of that point from the center of the shell. To find the electric field E at any point outside the shell, I want to find the electric field anywhere outside the shell. What do? I construct a Gaussian surface. You see how important it is? Now, the blue shell is the Gaussian surface. I want to find the electric field at this point. You see where I'm pointing? And therefore, I constructed a Gaussian shell that contains the points where I want to find the electric field. Alright. Now, if ER is the electric field at a distance R, this is the distance R, and if ER is the electric field at a point R from the spherical shell, this is the spherical shell we have of radius R, and we are now looking for electric field at a point distance R from its center. So let's say E sub R is that electric field. What will that electric field be? It will be, now, if ER is the electric field there, is that right? What is the total flux leaving the Gaussian surface? The Gaussian surface is this big shell. What is the radius of that shell? 4 pi r squared. What is the area of that shell? It will be 4 pi r squared. So the net flux leaving the Gaussian surface will be E, which is the electric field, that is flux per unit area, multiplied by the area of the whole shell. So phi net equal to E times 4 pi r squared. But according to Gauss's law, phi net must be equal to what? The net flux must be equal to 4 pi k times q inside, or q inside divided by epsilon naught. I've chosen this. Phi net equal to 4 pi k q inside. But phi net in this case is E times 4 pi r squared. So E times 4 pi r squared is 4 pi k q. You can see 4 pi and 4 pi will cancel. Therefore, what is E equal to? E equal to kq over r squared. Now, very important result. What it tells you is that the electric field at any point outside the shell behaves as though all the charge on that shell is concentrated at its center. Although the charges are distributed on the surface, the electric field at any point outside the shell behaves as though all that charge is concentrated at the center. The electric field at a distance r from the center of the shell, E sub r, is kq over r squared. That means as you go away from the surface, the field is going to decrease. Tell me, what is the electric field at the surface of our shell? The field at the surface will be kq over big R squared. This R will then be the radius R. You must know that. The electric field at a point on the surface will be kq over the radius squared, and that field will be at right angles everywhere. And I can also write it as 1 over 4 pi epsilon naught times q over r squared. Why? Because k equal to 1 over 4 pi epsilon naught. Now, this is the electric field at any point outside the charged shell. Any point outside the charged shell, you take the point here, the point here, point here, or anywhere, it will be 1 over 4 pi epsilon naught q over r squared. What is the field at any point inside the charged shell? Alright, if you take a Gaussian surface inside the charged shell, what will be the charge on it? Well, remember, the charges are distributed over the shell. So if you take a Gaussian surface inside, there will be no charge inside. And since there is no charge inside the shell, there will be no flux crossing that surface. If there is no flux crossing that surface, it means there will be no electric field. So what's the conclusion? The conclusion is that inside, at any point inside a spherical shell, the electric field is zero. So the electric field from the center to the surface, there is no electric field. Anywhere inside a charged shell, there is no electric field. Amazing, is that right? And the maximum electric field is at the surface, which will be kq over the square of the radius. And as you go away from the surface, the electric field will decrease, and given by 1 over 4 pi epsilon naught q over r squared. Alright, let's move on. Let's do a problem. A spherical shell of radius 6 cm carries a uniform surface charge density sigma equal to 9 nanocoulomb per meter squared. What is the total charge on the shell? Find the electric field at r equal to 2 cm, r equal to 5.9 cm, r equal to 6.1 cm, and r equal to 10 cm. Well, what's the first one? We got the radius of the cylinder is 6 cm, means 0.06 meter. What is the surface area of that cylinder, of that shell? Well, the surface charge density is 9 nanocoulomb per meter squared. Tell me, what is the area of the shell? What is the surface area? It's 4 pi r squared. And therefore, the total charge on the shell will be the area of the shell multiplied by charge per unit area. So Q equal to A times sigma, and you know both these quantities. That will be 4 pi r squared sigma. Using those values, 4 pi radius squared times sigma gives you 4.07 times 10 to the negative 10 coulomb. That is the total charge on the shell. Tell me, what is the electric field at a point 2 centimeter from the center of the shell? Knowing that the radius of the shell is 6 centimeter, a point at a distance 2 centimeter from the center is inside the shell. And what is the electric field inside the shell? Is zero. So the electric field at 2 centimeter will be 0. How about the electric field at 5.9? A point 5.9 centimeter from the center also is inside the shell. The field inside at that point will be 0. How about 6.1 centimeter from the center? Well, that is now outside. So we will use the formula for the outside. E equal to kq over r squared. K we know, Q we just calculated, and R is 6.1 centimeter, which is therefore ER equal to KQ. This is the calculated value of Q in the last slide, and this is the distance 0.061 squared. That is 984.4 Newton per coulomb is the electric field. What will be the electric field at a distance 10 centimeter from the center? Well, what all we need to do is replace the value of R by 0.1. Everything else is the same, and that is 366.3 Newton per coulomb. Alright, a very simple problem. Another one. A spherical shell of radius R1 carries a total charge Q1 that is uniformly distributed on its surface. A second larger spherical shell of radius R2. Now try and comprehend the meaning of this. That is concentric with the first, carries a charge Q2 that is distributed uniformly over its surface. Now use Gauss's law to find the electric field in the region R less than R1. That is the first one. R1 less than R less than R2. And R greater than R2. Remember, this R is the distance of a point from the center of the two shells. Alright, what should be the ratio of the charges Q1 by Q2 and their relative signs for the electric field to be 0 for R greater than R2? Sketch the electric field lines for the situation in B when Q1 is positive. Alright, let me show you the diagram. Here we have a spherical shell of radius R1. This is the first spherical shell of radius R1. Carries a total charge Q1. The amount of charge on that shell is Q1. And a second larger spherical shell that is concentric, means the center of the two shells are the same. Has a radius R2 and carries a charge Q2. Alright? So that makes it a little clearer now. Now, what do we want to find? Now, use Gauss's law to find the electric field in the region R less than R1. R less than R1 means inside the small shell. So what is the electric field inside the small shell? You can tell me immediately. Inside the small shell, the electric field is 0. Alright. For R less than R1, the points are inside the inner spherical shell, and so the field E equal to 0. For R1 less than R less than R2, in other words, a point in between the distance that R is greater than R1 but less than R2. That's what this means. A point such that its distance R is greater than R1 but less than R2 in a region between the two shells. Now, the points are inside the big shell. Is that right? So such points are inside the big shell and outside the small shell. The field at points at this region is purely due to Q1 because inside the large shell the charge is on Q2. There will be no field inside of the outer shell. So Q2 does not contribute to the electric field at this point. Only Q1 contributes. Now, and that will be E equal to K Q1 over R squared. So field at a point here will be E equal to K Q1 over R squared. For R greater than R2, a point outside both shells, is that right? R greater than R2, the points are outside both shells, and the field at a point somewhere here is actually due to both Q1 and Q2. Both Q1 and Q2 contribute, and we must now assume that the field at a point somewhere here behaves as though all these charges are concentrated at the center there. So what will be the electric field? E equal to K times Q1 plus Q2 over R squared. Now, so that is the electric field at a point anywhere outside. For the electric field to be 0 for R greater than R2, the total charge inside must be 0, because at any point outside, the electric field is produced by the combination of Q1 and Q2. The only way this electric field outside will be 0 happens when Q1 plus Q2 equal to 0. Now, when will that happen? It happens when Q2 equal to negative Q1. That means the amount of charge Q2 on the outer sphere is equal and opposite to the amount of charge inside. If one is positive, the other is negative. Therefore, Q1 over Q2 equal to -1. So the field lines in the region between the two, if the inside one is positive and the outside is negative, the field lines will look like these red lines. On the other hand, if the outside is positive and the inside is negative, the field lines will be directed in the opposite direction. Alright. Now, I'm going to leave this for you to read. We are going to use Gauss's law to find the field at a distance r from an infinitely long charge. Suppose I have a very long charge going to infinity on either side. I want to find the electric field at a point, a distance r from that infinitely long charge. Now, what is the method of finding the electric field using Gauss's law? Remember, I give you a method. In order to find the electric field at a point using Gauss's law, we need to first of all take a Gaussian surface. It's an imaginary surface. A Gaussian surface that contains the point where we want to find the electric field. Alright, tell me, if I want to find the electric field where I am pointing now, here, and this is the infinitely long charge, what kind of Gaussian surface is suitable for that purpose? Anybody got an idea? Well, the Gaussian surface can be a cylinder that encloses the linear charge. And on the surface of that Gaussian surface is the point where we want to find the electric field. Alright, let's do that. Now consider an infinitely long charged conductor which has a charge per unit length lambda. You remember that concept we talked about in the last class. The charge per unit length of this conductor, that infinitely long conductor, is lambda. And therefore, if I know the length of certain part of that charged object, can you find the total charge on it? If the length is L and the linear charge density is lambda, then the amount of charge on that length will be L times lambda. Now, here is the infinitely long linear charge, and I want to find the electric field at a point there. By symmetry, the field lines radiate uniformly outward if lambda is positive, or uniformly inward if lambda is negative. Is that right? I think that must be clear. If the charge carried by this linear charge is positive, all the field lines will originate or diverge from it. Or if the charge carried by this is negative, all the field lines will be converging to it. So you can imagine field lines coming out of it. Now we take a Gaussian surface, that is the beginning. If you want to find the electric field at a point, we take a Gaussian surface which is a cylinder enclosing a length L of the linear charge. And on the surface of that Gaussian cylinder is the point where we want to find the electric field. And that is the important thing. The point where we want to find the electric field must be on the Gaussian surface. Alright. Now if R is the radius of the cylinder, that's the radius. That means R is the distance from the point to the linear charge where we want to find the electric field. So if R is the radius of the cylinder, its surface area A will be 2 pi r times L. I suppose you understand that, is that right? Now, if this is a linear cylinder, what is its surface area? The surface area will be this length, which is the circumference of the circle, 2 pi r multiplied by the length L. In the same way, the surface area of this cylinder will be this length, that is the circumference of the cylinder of radius r, that will be 2 pi r multiplied by the length L, and that is the area of that cylinder. Okay. Now, if E is the electric field at a distance r, which is the same as the radius of our Gaussian cylinder, from the linear charge, then the net flux crossing the Gaussian surface, can you tell me or write down in your paper, what is the net flux crossing the Gaussian surface if the electric field is E? What is the definition of electric field using the concept of flux? I hope you haven't forgotten. Electric field is a measure of flux per unit area, and therefore the total flux crossing a given area will be electric field multiplied by the total area. So, if this is the Gaussian surface, which has a surface area, the spherical surface, the area of the surface is 2 pi r L, and if E is the electric field at a point on it, then the total flux crossing that area will be the total area multiplied by the electric field. Let's write that down. So phi net equal to 2 pi r L, that's the area, multiplied by the electric field. Now, what is the net charge inside the Gaussian surface? Can you tell me? Now, inside the Gaussian surface, there is a length L of the linear charge. Now, this linear charge has a linear charge density lambda. Alright? Linear charge density is lambda, and the length of the charge inside the Gaussian surface is L. What is the total charge on that length L inside the Gaussian surface? Alright? The Q inside, the total charge inside the Gaussian surface will be that L multiplied by lambda. So Q inside equal to L lambda. Well, we now know the net flux crossing the Gaussian surface. We know the amount of charge inside the Gaussian surface. Can you now write down the statement of the Gauss's law using these two? What is the statement of Gauss's law? Gauss's law says phi net, the net flux crossing any surface area, equal to Q inside divided by epsilon naught. Or if you want to state that in the form of K, it will be 4 pi K times Q inside. Alright? That is phi net equal to 1 over epsilon naught Q inside, which is the same as Q inside divided by epsilon naught. And of course, phi net is this 2 pi r LE, and Q inside is L times lambda. Let's use those values there, which gives me 2 pi r LE equal to L lambda divided by epsilon naught. And you can see L and L will cancel from both sides. And can you solve for E from here? What is E equal to? Now when L and L goes, we get E equal to lambda divided by 2 pi r epsilon naught. Or we write it like this. E equal to lambda divided by 2 pi epsilon naught times 1 over r. Now why did I write it like this? Because lambda divided by 2 pi epsilon naught is a constant and r changes. If I take the point here, that R will be that distance. So R is the only variable, all other quantities are constants. It's a very important relation if you want to use it for solving problems. Okay, let's go and look at the charge and field at the surface of a conductor. Now, suppose I have a charged conductor. Now, here is a conductor. If I charge this, in other words, if I give some excess charge to this, tell me, where do you think the excess charges are going to reside? Now, will there be any excess charge inside this conductor? Well, will there be any charge inside the conductor? Well, remember, these charges are all like charges and they would like to go as far away from each other as possible. Not only that, that means they will not like to stay inside the conductor. Now, when they all want to be as far away from each other as possible, they will all end up on the surface. Which suggests that if you have a charged conductor, then all the charges must reside on the surface of the conductor. Charges cannot reside inside the conductor, because if charges are inside the conductor, they will be forced to move by the electric field produced by the other charges. Okay, so a conductor allows free charges to move within itself, is that right? That's why we call it a conductor. A conductor will allow free charges to move within it. If there is an electric field inside a charged conductor, it will make free charges inside it to move, causing an electric current to flow. Well, what does that mean? It means if I have a charged conductor, you cannot have an electric field inside a charged conductor. Because if there is an electric field inside the charged conductor, the free charges inside will all be moving because of the electric field. That means there will be perpetual motion of electric charges inside, which will set up an electric current. And you know, in reality, it doesn't happen. So what is our conclusion? Now, that means this causes redistribution of electric charges in such a way that there is no net electric field inside the conductor. So, when you have a conductor that is given an amount of charge, these charges will redistribute themselves so that there will be no net electric field inside the conductor. And when they redistribute, where are they going to be? When this happens, all the free charges will reside at the surface of the conductor. A very important information. So all the charges, all the free charges on a conductor will reside only on its surface. And also, there will be no electric field inside a conductor. There cannot be an electric field inside a conductor. If there is an electric field, it will make the free charges in it to move. Now, we can use Gauss's law to show that when there is no net field inside a conductor, the net charge inside the conductor will also be zero. Anywhere there is no net field, there will be no net charge. Is that right? If there is no net field, the net flux crossing a given surface will be zero. That means the net charge in that surface will be zero. So what is the conclusion from the discussion we had so far? If you have a charged conductor, all the charges will reside on the surface. And what will be the electric field inside that charged conductor? The electric field inside a charged conductor will be zero. Alright, so we can conclude the following about a charged conductor. I'm going to put down those conclusions for you. Now here I have a charged conductor. Now all the charges reside on the surface. Now that means the electric field, there will be no electric field inside the conductor. There will be an electric field on the surface of the conductor. And can you tell me, what is the direction of the electric field on the surface of the conductor? You see, let me take my disc again. Now, what is the direction of the electric field on the surface of the conductor? The direction of the electric field has to be at right angles to the surface. Why? Because if the field is, say, at an angle like this, electric field is a vector quantity. If it is an angle like this, there will be a component of that field along the surface and a component at right angles. Now remember, if there is a component of the electric field along the surface, that electric field will make the electric charges to move on the surface. Well, since that doesn't happen, we know that there will be no electric field component along the surface of the conductor. That forces us to believe that field at any point on the conductor is always at right angles. Anywhere you take a point on the surface of the conductor, the electric field will be at right angles. An important information you should not forget. So what are our conclusions? One, all the charges reside on the surface of a charged conductor. You have a charged conductor, all the charges, all the excess charges will reside on the surface of the conductor. Our second conclusion, the electric field inside a charged conductor is zero. There will be no electric field inside a charged conductor. What else? The electric field at the surface of the conductor is at right angles to the surface everywhere, irrespective of the shape of the conductor. You can have bumps and valleys on the surface of the conductor like this. You see that? But irrespective of the shape, if you take any point on the conductor, the electric field at that point will be at right angles to the surface. Very important conclusions about a charged conductor. Alright, let's now do a problem. An uncharged metal slab has square faces with 12 centimeter sides. It is placed in an external electric field that is perpendicular to its faces. The total charge induced on one face is 1.2 nanocoulomb. What is the magnitude of the electric field? Now, did you understand that question? We have a slab. Now, here is a slab. There you go. A slab is placed in an electric field. Is that right? This is the slab placed in an electric field. That means the field lines go like this. Now, if the field lines are in the positive x direction, as I just pointed out, it means the negative charges on this conductor will all accumulate on this surface of the slab, and positive charges on the other side. Why? Because negative charges that are free to move will always move against the direction of the electric field. So if there is a field directed that way, then the free negative charges inside the slab will move as far away in the opposite directions, making this phase of the conductor negatively charged and that phase positively charged. And that is what is told in the problem, that the total induced charge on the phase. So as a result of placing this slab inside the electric field, there is an induced charge on each phase. You understand why the induced field charge is there. And that induced charge is 1.2 nanocoulomb. And what do we want to find? What is the magnitude of the electric field? What is the magnitude of the electric field? Well, that is actually a very simple question if you figure out. Now, here is the slab, as the electric field is in that direction, say positive x direction. This phase of the slab gets induced negative charge, and the other phase gets induced positive charge. You know that this happens because of the polarization of charges inside the conductor. The surface charge density on the metal slab is sigma equal to Q over A. Is that right? That is the definition of surface charge density. Now, if the surface area is A and the amount of charge is Q, then the surface charge density will be Q over A. Now, do you know the area of one phase of this slab? The slab is a square of 12 centimeters side. That means that area will be 0.12 squared, and the induced charge on it, Q, is 1.2 nanocoulomb. So that is 1.2 times 10 to the negative 9. You see how quickly we can use that information to obtain a vital quantity, which is the surface charge density on this slab. The surface charge density now equal to how much? 8.33 times 10 to the negative 8 coulombs per meter squared. Now, if you recall, the electric field outside a charged object, charged conductor, is related to the surface charge density. Do you remember that one? The field outside a charged conductor is E equal to sigma over epsilon naught. Well, once you know that, you can now find the electric field because you know sigma, you know the value of epsilon naught. Therefore, E equal to sigma, which we just calculated, and epsilon naught is 8.85 times 10 to the negative 12. That is 9,416 Newton per coulomb is that electric field. A very neat but simple problem. Alright, let's go on and do one more problem. If the magnitude of electric field in the air is as great as 3 times 10 to the 6 Newton per coulomb, the air becomes ionized and begins to conduct electricity. This phenomenon is called dielectric breakdown. Now, a charge of 18 microcoulomb is to be placed on a conducting sphere. What is the minimum radius of that sphere that can hold this charge without dielectric breakdown? Now, I think you must understand the meaning of dielectric breakdown. You see, normally air is a good insulator. It will not allow electric charges to flow through it. But when will ultimately electric charges will flow through it? When the electric field becomes very strong, when the electric field is very strong, a strong field can rip the atoms of the air into pieces, making them individual charges. That means air will then become ionized. An ion is a ripped apart atom, so that positive and negative charges occur separately. And when these charges move in the opposite directions, you have an electric current. So, air, which is normally a very good insulator, can be made conducting by a very large electric field. We know that, especially those who live in Florida, that Florida is the lightning capital of the world. What is lightning and thunder? It's nothing but the electric charges that are accumulated in the clouds, creating a great big electric field. And when that electric field is very large, it rips the atoms of the air molecules, producing ions, which then produces a great electric current that flows into the earth. Now that is what lightning is, and thunder. So that happens because the air which is a dielectric, breaks down and becomes a conductor. And when will that happen? When the electric field is as high as 3 times 10 to the 6 Newton per coulomb. So our question is, we have a conducting sphere, and we need to place some charge on it. 18 microcoulomb of charge are going to be placed on the sphere. Now remember, the electric field created by charge on a sphere, in other words, the electric field on the surface of a conductor. Anybody recall the equation for that? Well, before coming to watch a lesson, I would expect that you have got the background that we discussed in a couple of lessons ago. Now, if you have a conductor, a spherical conductor that carries a charge Q, a spherical conductor of radius R that carries a charge Q. Now, I have been using this basketball every day. Suppose this is a spherical conductor that carries a charge Q. What is the electric field at its surface? The electric field at any point at its surface is KQ over R squared, where Q is the amount of charge and R is the radius. Now, that KQ over R squared cannot exceed this value. If it exceeds that value, then dielectric breakdown will happen. Our question is, what should be the minimum radius? What is the minimum radius of a sphere that will hold this charge so that the electric field will not exceed that value? Okay, let's do that now. So, the amount of charge is 18 microcoulomb, 18 times 10 to the negative 6 coulombs. We need to find the value of R, which will produce an electric field equal to 3 times 10 to the 6 Newton per coulomb. In other words, it will not produce an electric field greater than that. This is the maximum electric field it will produce. If R is the radius of the sphere, then sigma, the surface charge density, will be Q divided by 4 pi R squared. Is that right? Yes, because Q is the total charge on the sphere. 4 pi R squared is the surface area of the sphere. Therefore, sigma, the surface charge density on the sphere, will be Q over 4 pi R squared. And you know Q, we know 4 pi, but we don't know R. So we're going to leave this in terms of R. So that will be sigma equal to 1.43 multiplied by 10 to the 6 over R squared. And what is the expression for electric field just outside a conductor? Well, the expression for electric field just outside a conductor is sigma over epsilon naught. Let's now the electric field En just outside the conducting sphere is sigma over epsilon naught. That means this value of sigma has to be this. So that will be, I've replaced this sigma by that value. That is 1.43, not 46. 1.43 times 10 to the negative 6 over r squared divided by epsilon naught is this value. And we know this E. What is that E equal to? 3 times 10 to the 6. And now this quantity cannot be greater than 3 times 10 to the 6. So we replace that En by 3 times 10 to the 6 and then solve for R. So can you solve for R? R squared equal to this quantity divided by 8.85 times 10 to the 12 times 3 times 10 to the 6. And put that in your calculator, that gives you 0.055. If that is R squared, R equal to 0.235 meter, which is 23.5 centimeter. Alright? That has been a good problem. Well, but that is the conclusion of